Hey everyone! So in this video I like to talk about combining like terms. So sometimes when we are trying to create an expression to represent some scenario, to model some scenario, there might actually be multiple expressions that correctly represent that scenario. Here, let me show you an example. So here we're given this rectangle with a side length of 6 and another side length of some unknown measurement x feet, and we're asked to write an expression for the perimeter of this rectangle. And so let me remind you that the perimeter, this is just the measurement of the boundary of this shape. It's the sum of all the side lengths. And so if I wanted to write an expression for the perimeter of this rectangle, well, I just need to add the side lengths together. So I can add this side length x with this side length x as well, so x plus x. I can add on this side length plus 6, and this side length on the right plus 6 again. So this is one expression for the perimeter of this rectangle. And you might also be familiar with the formula for the perimeter of a rectangle. Sometimes it's seen as 2 times the length plus 2 times the width. Right, because here we would be adding on 2 sets of whatever measurement x is with 2 sets of whatever measurement the width is, which in this case would be 6. So another valid expression is 2x, 2 times x, plus 2 times 6, that's 12. Right, so this is another expression that gives us the perimeter of this rectangle. And I'm sure there are other expressions we can write down, but maybe we'll use these for now. So here, these are 2 valid examples for the perimeter, and these are examples of what I like to call equivalent expressions. And so what makes these 2 expressions equivalent? Well, they represent the same idea, right? They're here representing the same perimeter of this shape, and what that really means is that no matter what value I plug in for x, I should get the same result between these 2 expressions. If they're going to really represent the same quantity, they should give me the same result every time as one another. Right, so let me show you exactly an example of that. Right, so here if we let x be equal to 7, and we replace that into the first expression, our expression x plus 6 plus 6, well then what we get is 7 added on with 7, plus 6 plus 6, and this gives us, well, this is 14 plus 6 plus 6, this is 20 plus 6, and then finally this is 26. Now, if we take this other expression that I'm claiming to be equivalent, right, or really represent the same perimeter, it should give me the same result, right, if it's measuring the same thing. And so if I replace an x value of 7 into this expression, although it looks a little bit different, we end up with the same result, right? First we do order of operations, tells us to do multiplication. 2 times 7 is 14 plus 12, and 14 plus 12, that gives me 26, right? I add on the 10 first to the 14, and then I add on 2 more to give us 24 to 26. Okay, so we get the same result from plugging 7 into both of these different expressions. Maybe let me show you that actually it doesn't matter what number we replace x by, we should get the same thing if they're really representing the same idea of this perimeter of our shape. Right, so let me plug in x is equal to 10 into the first expression, giving us 10 plus 10 plus 6 plus 6. Right, this gives us 20 plus 6 plus 6, or 26 plus 6, and then 26 plus 6, that's 32. Right, so here, what this is saying is that we're finding the perimeter when x is equal to 10, when this side length here is 10 feet. Okay, and so what happens if we plug this into the other expression? Well, here we get 2 times 10 plus 12, and 2 times 10, that's 20, and if we add 20 and 12 together, well, if I add on 10 of that 12, I get 30, and then adding on 2 more gives me 32, and we get that same result as we saw before, 32. And this is what I really mean by these expressions being equivalent, is that no matter what number I plug in for the variable x, the two expressions are going to give the same result as one another. And so let me write that down, it's an important idea. So two algebraic expressions are equivalent if they produce the same result as one another. For every value of the variable. So the idea is that no matter what number I plug in for x, here we chose 7 and we chose 10 just to pick some random examples, but really the idea here is that no matter what I plug in for x, I should get the same result if these two expressions up here are really equivalent, representing the same idea. So how can we tell if two different looking expressions are equivalent? Well, we saw in the last example that two equivalent expressions should give us the same result as each other for every value we plug in for the variable. And so we can use this idea to test whether or not two expressions are equivalent by just plugging in different values for the variable and seeing if the two equations give the same result for many different values. Right, so here we can see whether or not two expressions are equivalent if we plug in different values for the variable and see that the two expressions always give the same result as one another. They always agree. And so if there's even one time that the two expressions don't agree, so if there's even one time that you can find a value of the variable where the expressions don't come out to the same result, this means that the expressions are not equivalent. And so here let's take a look at an example. So let's take the expression 2 plus 5x and 7x, and let's try and convince ourselves whether or not these two expressions are equivalent. And so what we're saying up here is that what we should do to tell whether or not they're equivalent is just plug in different values for x and see if the two give us the same result as one another every time. And so here I'm going to plug in an x value of 1. Right, so what happens when we let x equal 1? I would get 2 plus 5 times 1. For this left expression, and this is 2 plus 5, right, because we do the multiplication first before the addition, and this gives us 7. Well, here's 7 times x. Well, if we're letting x be 1, then this is just 7 times 1, which is just 7. So we get the same result here from this first expression and this second expression when we plug in x is equal to 1. And so are these two expressions equivalent? Well, for the two expressions to be equivalent, they need to give us the same result from every single possible value we plug into the expressions. And so here, if I check another one, let's do x is equal to 3. If they're equivalent, then they should give us the same result for this too. And so if I plug in 2, or if I plug in 3 into this expression, what do we get here? Well, we get 2 plus 5 times 3. 5 times 3 is 15. And this is 17. And then what does this second expression give us? Well, 7 times, we're plugging in 3 for x in this example, and 7 times 3 is 21. And 21, this is not the same value as 17, even though we plugged in the same x is equal to 3 in both expressions. So what this is telling us is that these are not equivalent. If we could even find one example where they don't give us the same result, the two expressions are not equivalent. And so in the last example, we saw that here the expression x plus 6 plus 6 was equivalent to the expression 2x plus 12. So we only checked two different values, but I assure you that no matter which value you check for the variable, we get the same result every time. And so here, this left expression comes out to the same value as the right expression. We can really reasonably write an equality sign between them. They're going to give the same result every time. And one thing I want to point out is that this equality sign here, this equal sign is quite different than the equal sign we're used to writing in our equations, right? So this equality sign, it's saying these two expressions are equivalent, right? So this is equality representing equivalent expressions. Right? Here, this is saying that the left side always give the same value as each other, regardless of the variable, regardless of the value of the variable. So another thing I like to bring up with this other example here, the fact that x plus 6 plus 6, this is equivalent to 2x plus 12. Here, this expression on the right side of this equation, it feels like a simpler expression to work with. And so this brings me to my next point, is that one of the big goals with algebra is to learn how to take different kinds of expressions and rewrite them as simpler but equivalent ones. And so this process here of rewriting an expression as a simpler but equivalent expression, this is typically called simplification or simplifying an expression. So one of the big goals with algebra is to learn how to take different kinds of expressions and find ways to rewrite them as simpler equivalent ones. And so one of the common ways that we can do this, or we can rewrite or simplify expressions, is we can do this by combining like terms. And so that's what I like to talk about for the rest of this video is what are like terms and what does it mean to combine like terms. So let's explore this. So like terms are terms with identical variables factors. So let me tell you what I mean by that. Let me showcase what I mean by that with examples. So here, if I have something like 8x and negative 3x, right? So this word factors here, and if you don't remember what this word factors means, it just means when you're multiplying two things or three things or so on, what are those things being multiplied? What's being multiplied together here is 8 and x in this first example, and negative 3 and x in the second example. And so we might call 8 a factor of this term on the left, and x a factor of that term on the left. Or we might say negative 3 is a factor of the term on the right, or x is a factor of, and x is a factor of the term on the right. And so here when we say like terms are terms with identical variable factors, here we're just saying what are the variable factors, and these terms are like terms if those variable factors are the same. So here we have a variable factor of x and a variable factor of x. So these are examples of like terms. Right, so another example is something like 17a and just a itself. Right? So if we have the variable a, if I look at this term on the left, the only variable is the variable a. There's only one factor of it, and then on this term on the right, well, again, the only variable is this variable a. So here, these two are examples of like terms. What about 3xy and 5yx? So are these like terms? Are the variable factors identical? Are they the same between these two terms? Well, if I look at this expression on the left, this term on the left, what are the variable factors? Well, there's this factor of x and there's this factor of y. And then on the right, well, there's this factor of y and there's this factor of x. And here, the order of multiplication doesn't matter. It doesn't change here. They both have factors of x and y, and just a single factor. These are both like terms. So here, maybe I'll put a little check mark between all of these. These are all examples of like terms. And sometimes I think it's illustrative to include some non-examples, right? So here, if I have, let's say, negative 4a and 12b, if I look at the variables that are multiplied in this expression on the left, the term on the left, it's 4 and this a, and here I've got this 12 and this b. Well, the variable factors in these two terms, they differ, right? They're not the same. So here, these are not examples of like terms. And maybe let's just keep going with some non-examples. Let's do 5y and 3. So here I look at these two expressions, these two terms, and this first example, it has this variable factor of y, and this second example, there's no variable factor, and so these are not equivalent not like terms. Okay, so here we need to see the same variables, and we need to see identical numbers of their factors. Here's another example. So you might not be familiar with exponents yet, so if you aren't, then that's okay, don't worry about this. But here, if I have x and x squared, or in other words, two factors, that's what squaring means. We'll talk about this in the future. But this is just saying that there are two factors of x here, two x's being multiplied. And there's just one here. So although they're the same variables, they're not the identical number of factors of that variable in both of these terms. And so here, these are examples of not like terms, despite them being or consisting of the same variable x. So let's continue developing some more language. Here, let me look at another example here. I'm just going to write some long, messy expression with a lot of variables. So 4x minus 7y plus 10 plus 3xy plus 15y minus yx. So this is a long, messy expression, but it's just here to illustrate some ideas, some new language. So, we call these things above, we call them like terms. And I defined this word terms a while ago. But let me just remind you what terms mean. So when we're adding and subtracting a bunch of things together, each one of those parts of our expression that are being added or subtracted, those are examples of terms. So here, maybe I'll just write this below, that terms are parts of an expression that are added or subtracted together. Right, so here, if I look at this expression above, this long string, this 4x is an example of a term, 15y is an example of a term, 10 is an example of a term, 3xy is an example of a term. When we have subtraction, we actually include that subtraction to the term on the right. Here, I look at this minus 7y as a term, and this minus yx, that's also a term. So these are all the terms in the above example. It's just the parts of our expression that are separated by addition and subtraction, and then we always have to keep in mind that subtraction, that's associated with the term on the left. We always kind of attach it with that term. So I don't think of this term as 7y, I think of it as minus 7y. Okay, so that's what terms mean. What else did I want to talk about? Oh yeah, let's continue this idea of like terms. So here, if I look at 4xy, are there any like terms with this it's 4x, are there any like terms with 4x in this expression here? Well, I look all throughout, and here, there's this 3xy. That's not a like term with 4x, right? Because there's this extra factor of y here. Whereas the first term, 4x, doesn't have a factor of y. And so here, these are not like terms. So let me keep looking. 15y minus yx, no, there aren't any like terms with 4x. Minus 7y, so we said, this minus sign that's associated with that 7y as a term. And we want to look for other like terms here. Well, here we just want to find any terms that contain only a y factor as its variable factor. And so here there's another y term, it's 15y. So that's like terms with my minus 7y. 10, so this is a term. Are there any like terms? Well, the like terms with 10 are going to be the terms with no variable factors. And this is the only term with no variable, so it doesn't have any like terms. Here, this 3xy, are there any like terms with this one? Well, there's this minus yx that, although it's in a different order, it's got the same variable factors, y and x, and only one of each. So these are like terms. So another term, or another piece of language that'll be relevant to us, is this notion of a coefficient. So the numerical factor, in a term is known as the coefficient of the term. And so this is a word that's used very frequently and you want to be very comfortable with. So all it's saying is it's, if you have a term, it's the number that's being multiplied in that term. Right? So here, if I look at this first term, 4x, what's the coefficient of this? The coefficient of this term is just the number 4, because it's the number that's being multiplied in this term. So 4 is the coefficient of 4x. What about this next term? So what's this next term's coefficient? Here, you might say it's 7, but actually, again, we associate that subtraction with this term. And so you can read this off as negative 7 as the coefficient, right? Because we can always think of this subtraction here, right? Minus 7y. If we're, it's kind of in the middle of an expression. This is really the same as adding negative 7y, right? Subtraction is the same as adding the opposite of the following term. And so I can always think of subtraction as, I can look at it as this negative of adding the negative of that next term. And so here, if I look at this, the coefficient of this term, this minus 7y, I would read it as negative 7 as the coefficient. So negative 7 is the coefficient of minus 7y. Here, what about this next example? What about xy? Right, what's the coefficient of xy? So this has coefficient. Do you have any guesses? So here, there isn't any number in front. You might think maybe 0, but actually it's the number 1. Right, so I can imagine, so x times y, that's the same as 1 times x times y. And so here that's really telling us that this coefficient of this term here has a coefficient of 1. Right, if I try to write this as a coefficient of 0, if I try to think, there's no term or there's no number in front, maybe the number is 0, well, 0 times anything is 0, and all of a sudden this term would be deleted, right? There's nothing there. But 1 times this term is the same as itself, the same as this term that we started with. And so the coefficient is 1. Okay, so now we have all of the ideas and the language necessary to talk about how we combine like terms. And so here we can simplify an expression by combining like terms And combining like terms, what does that mean? It just means add or subtract the coefficients of the term. And here we also have to keep the variable, or the variables, maybe there's multiple, the variables the same. So here, combining like terms is this idea here. If we have any like terms, we can combine them by adding or subtracting the coefficients of the term and keeping that variables of the term the same. Right, so here, let me just say, let me give a few examples. So let's say we want to simplify the following expressions. So maybe I'll just write them one at a time. 5n plus 3n. So I have these two terms here. They're like terms, right? They have the same variable factor. The only variable factor is n. And so these are like terms. And what I'm saying is that to add these two terms together, if we're trying to simplify this expression, right, as a simpler equivalent expression, well, what we do is we just add the coefficients together, the numbers in front of these terms, the numbers being multiplied in front of these terms. Well, that's 5 and 3 added together to give us 8n. Right here we add the coefficients, but we keep the variable, leave it exactly the same. So that's it. That's all it is, and it's giving us an equivalent expression. 8n is really the same as 5n plus 3n. It gives us the same result no matter what value we plug in for n. If I have negative 4y minus 3y, I have these two like terms and I'm trying to add or subtract them, in this case subtract. Here I can subtract their coefficients to figure out the result of this, or to see an equivalent but simpler expression. And so here to subtract these coefficients, maybe I'll write this as an addition problem because it might be simpler or easier to perform addition than subtraction. So right, negative 4y plus negative 3y is the same as the subtraction problem we see above. And to add these two problems, or these two terms together, because they're like terms and I can combine them, I can add these two together and to simplify this expression. Here I add negative 4 and negative 3 together and then keep that variable. So negative 4 plus negative 3, that's a negative 7. I owe $4, I owe $3, so together I owe $7. And the variable is still y. And so here when I write this equality sign, it's just saying I'm writing my previous expression as an equivalent expression that's possibly simpler. And so here, this equality is saying I've simplified my expression. It's the same at heart, just possibly different looking. And let's do another one. Let's do negative st plus 8st. So again, we see the same variable factors st. There's no extra ones involved. They're not missing anything from one to the other. So here, if I want to simplify this expression, I want to combine like terms. Well, I just add their coefficients. And here, this left term has a coefficient of negative 1. The right term has a coefficient of 8. And so adding those together, I have negative 1 plus 8 sets of st. And so negative 1 plus 8, I owe $1, but I have 8. I can pay a little bit of that off and I'd still have $7 left over. So this is 7st. I'm just adding the coefficients. And then let's do another example here. 5b minus negative 11b. Again, these are like terms. I can combine these like terms. And I can rewrite this 5b minus negative 11b, right? Subtraction is adding the opposite of the following term, so I can write this as plus, the opposite of negative 11b is plus positive 11b. And then adding these two terms together, I'm just adding their coefficients to get 5 plus 11, that's 16b. And again, I can only perform this simplification if they are like terms. Their variables are the same quantity of those factors, and the exact same factors themselves. So, if I had an a on one side and a b on the other, I couldn't perform this simplification. I can't just add the coefficients if they're different variables, or if they're missing variables from one to the other. Okay, and then let's look back at this example we saw above. This is kind of a very involved looking example with many different variables and terms. But now that we have all this language and these ideas, we can simplify this expression. So here, let's simplify this. And earlier I said that when we have an expression with all this subtraction, we can rewrite that subtraction as adding the opposite, right? So here I can look at this term as plus negative 7y, and I can look at this term at the end as plus negative yx. And remember that when we add two quantities, the order of addition doesn't matter. If I add 2 and negative 5, that's the same as adding negative 5 and positive 2. I can shuffle all my terms around if I'm adding things together. You get the same result. And so here I can rearrange these to put all the like terms together and add those together and combine those like terms and simplify. So here, we saw that 4x didn't have any like terms. So we still have this 4x. Negative 7y, that's like terms with this 15y, and so adding those together, I get 8y, right? If I owe $7 and I have 15, I can pay that off and I have 8 left over. And then I still have this 10, there's no like terms with that, and then this 3xy and this minus yx, I can combine those to see that there's two sets of xy, or you can write it as yx. That's really the same idea. So I told you one way of simplifying expressions through combining like terms, but I didn't tell you why we can combine like terms. Right, so here, let me just show you an example of two terms we can't combine because they're not like terms, right? So here, as we saw in one of the first examples, 2 plus 5x, these aren't like terms, and adding their coefficients together, 2 and 5, to get 7, that doesn't give us an equivalent expression. We saw that we do not get the same results generally from 2 plus 5x and 7x. Right? We plugged in 3 and we saw 1 gave us 17 and 1 gave us 21. They're not equivalent. And so, if I see that expression on the left, 2 plus 5x, I can't add 2 and 5 together to give me anything reasonable. And so we just don't do it, at least if we're trying to simplify. But yeah, let's talk about why it makes sense to combine like terms. So here, if I have 2x plus 3x, right, we're saying that this should equal, if we were to combine like terms, this should be 2 plus 3x, this is 5x. Right, so maybe let's justify why this makes sense. Like if x is the cost of a pineapple, just to give a very concrete example, we go to the store and x is this unknown cost of this pineapple. What does 2 times x mean? It means I'm paying for 2 sets of pineapples. I'm really paying this x price 2 times. And what does 3x mean? Well, it means I'm paying for 3 sets of pineapples. I'm paying that cost 3 times x plus x plus x. And if I'm adding these all together, that's just like saying I'm paying this cost, 2 times and then 3 times. Well, that really means I'm paying the cost a total of 5 times, right? This is the same as 5, or maybe I'll just write it, yeah, I'll write it like this, 5x, right? I'm paying that cost 5 times. And so really it does make sense that 2x plus 3x is the same as 5x, really adding those coefficients together and keeping that variable the same. And you can confirm this with very concrete numbers, right? So if I plug in, or if I think of x as representing 4, maybe the pineapples cost $4. If I buy 2 of them, that's like adding 4 plus 4. And then if I buy 3 of them, well, that's like adding 4 plus 4 plus 4 plus 4. No, I think I said that too many times. And then adding all those together. And we can see we get the same result, right? So here this is 2 times 4 plus 3 times 4. We're saying this is the same as 5 times 4, which is 20, and below we get 4 plus 4 plus 4 plus 4 plus 4. This is also 20. Right, so this is just to illustrate that combining like terms makes sense. And here I also want to illustrate that trying to combine unlike terms doesn't make sense. Right? If I have 2x plus 3y, maybe this time, x still represents the cost of a pineapple, but y represents the cost of a mango. Well then, what does 2x represent? It's like paying for that cost of the pineapple 2 times. And 3y represents paying for the cost of the mango 3 times. And adding them together, I do get a reasonable value, but I don't get any reasonable value by adding 2 and 3 together, right? Right. If I have 5 what, right? 5 costs of a pineapple doesn't make sense. 5 times x doesn't make sense, because we're not buying 5 pineapples. We're buying some pineapples and some mangoes. And 5y doesn't quite make sense because I'm not buying 5 mangoes, and so that wouldn't give me the same value as what we're expecting here. And 5x times y, this also doesn't really make sense because x times y doesn't really mean anything. Multiplying the cost of mangoes and pineapples together isn't really giving me anything sensible. So really, we just can't combine unlike terms to simplify our expression. We can't write this in any simpler equivalent way. Right? So here we can't add any unlike terms together to make a simpler expression. And so if you were asked to simplify something like 2 plus 5x, where we have unlike terms, or 6 minus 3y, negative 6 plus 4xy, I'm just showing a bunch of examples of non-like terms being added or subtracted together. Well, here, you just wouldn't add the 2 and the 5, or the 6 minus the 3, or the negative 6 and the 4, and the 2 and the 3 here. These are just they're all unlike terms, and we cannot simplify these expressions any further. So really, if you're at this stage, you have these expressions, and you want to simplify further, well, actually you can't. So we would just leave these as is. They represent the idea that they're representing as simply as they can.